the next talk by Dvir Ginzburg and Dan Raviv. The talk will be given by Dvir.
Hi, I'm Dvir Ginzburg, a master's student under the supervision of Dan Raviv in the Geometric Deep Learning Lab, and I'm going to present you our work named Cyclic Functional Mapping, Self-Supervised Correspondence between Non-Isometric Deformable Shapes. The shape correspondence problem is one of the most fundamental problems in computer vision. It started in 2D vision, in the panorama problem, for example, where we had multiple views of the scene and we would like to align them together to a single image. But nowadays, in video, 3D, and virtual reality applications, we have a much more complex task, as we will need to align multiple objects that move and differ in different directions and types within time. Thus, from having to solve only a set of fixed number of parameters, like translation and rotation, we will have a complex, nonlinear optimization function. To further understand the shape correspondence problem, we will see the different deformations that can be applied on top of those objects. But first, we will need to have a quantization step, where we turn our continuous surfaces, our objects, for example, humans, to graphs. Those graphs, by defining vertices and edges, are called meshes. On those meshes, we can define different deformations. The first one, the easiest, is the rigid deformation, similar to the panorama problem, where only a fixed number of parameters is able to create a coherent alignment. The second one, the non-rigid deformation, is much more complex, while the global structure may vary dramatically, locally, the distance between each two adjacent vertices stays the same. We call such deformations epsilon isometric, and examples can be seen as in the image in the middle, where a human is raising his hands, objects, for example, animals running, etc. On top of the non-rigid deformation problem, we have the stretchable problem, the stretchable correspondence problem, a problem that, to the extent of our knowledge, not have been researched yet by data-driven solutions in the spectral domain. In the stretchable correspondence problem, not only that the global structure may change, but also locally, the pairwise distances may vary. For example, when comparing different objects, while the evolution of an object itself, and we will see further examples later on, or under stretches, global and local scalings. One of the first papers, one of the most revolutionary papers that tried to tackle this problem in the spectral domain was functional maps. Functional maps provided a way for, instead of matching our high-resolution meshes, that in our cases involve more than 100,000 vertices, to only align their spectrums. And again, in our cases, 100 most significant eigenvectors are sufficient to fairly represent the shapes. In the functional maps pipeline, by having a subset of ground truth correspondences in advance, we can set indicator functions on top of those ground truth correspondences, decompose the functions using, for example, the Laplace-Beltrami operator, and then find the alignment matrix C, and we will use C later on, to align the spectrums together. As you see in the example below, while the two spectrums may differ completely, after having the alignment matrix C, the spectrums are aligned. Then, by having C and reprojecting back to the spatial space, we will have the dense correspondence without specifically solving it. Although remarkable, the functional maps pipeline had a severe problem, which is needing the ground truth correspondences at inference time, a subset of them. Deep functional maps, which is a deep learning framework that was proposed by Or Litani, a student from Tel Aviv University 2 years ago, showed how you can remove the need of ground truth correspondence completely using a fully supervised deep learning algorithm. Instead of having the subset of ground truth correspondences, they learned the best pointwise descriptors, thus solving C in an approximate manner. They also presented P, which is the soft correspondence matrix. For intuition, P is simply the probability. For example, Pji is simply the probability that vertex I in the source corresponds to vertex j in the target. Using P, they presented their supervised loss function, which simply penalizes the confidence of P of a given correspondence by the distance from the ground truth correspondence. Last year, a group from the Technion showed that you can discard the need of supervision completely. They showed that if you assume isometry between the graphs, which means the graphs are isomorphic, and we'll get to that assumption more on later, you can use the Gromov-Hausdorff distance theorem, and instead of finding the correspondence in the spatial space, which is rather complex, that ensures the isomorphism, you can find a correspondence that minimizes the pairwise distortion function. And they sit here today, and they will present their work more thoroughly. The problem is that the isometry constraint is simply infeasible in most practical applications. As we mentioned before, when matching males to females, short to tall people, the isometry constraint is not satisfied. Or even when talking in the autonomous car systems, where the acquiring system itself moves, the objects are being transformed by local and global scaling procedures, thus again, not having the isometry constraint. The question we asked ourselves is, can we do better? Meaning, can we have an unsupervised pipeline for the dense correspondence regime and be stretch invariant? And the answer is that we can. We present a cycle consistent loss. By learning both the correspondence from the source to the target and from the target to the source, we compose the two to have our bidirectional mapper. We also presented our cyclic distortion function that simply calculate the differences between all the pairwise distances in the source and the pairwise distances after applying the bidirectional mapping. I must emphasize that both P and P tilde are adjoint, meaning they come from the same CMEs architecture with shared weights, meaning that, for example, P cannot contract a head to a nose, and P tilde expand back the nose to the full head, as they must learn invariant structures. By using our cyclic distort function and having P, the soft correspondence from the deep functional map paper, we presented Q, which is simply the composition of P tilde on top of P, which P tilde is the soft correspondence from the target to the source. By plugging Q into our cyclic loss, into our cyclic distortion function, we have our cyclic loss. Looking at the cyclic loss, one must see two important points. The first one is that unlike previous unsupervised regimes that assumed isometry between the graphs, we do not punish on the divergent between the source and the target, meaning that we do not have dy, which is the geodesic distance matrix of the target shape, in our loss function. This fact is what lets us to not assume isometry between the shapes. On the other hand, the fact that let us not to learn, the fact that ensures that we will not learn any composition of P and P tilde that generates the identity function, is that P and P tilde are not any set of learnable parameters. P and P tilde are the reprojection of C, which is indeed learnable, on top of P and Xi. and phi and xi are not learnable, but are the decomposition via the Laplace-Beltrami operator, which is heavily induced by the geometry of the shapes. Thus, on the one hand, we do incorporate the geometry of the shapes, but on the other hand, do not penalize on the difference in isometry between them. And this is an example we'll get to on in a few more slides that show how previous unsupervised methods that assume isometry simply break when we present scaled versions of the same object. Our learner can be invariant to such deformations. Our architecture. First, both shapes from the left and the right go through the multi-scale layer, where we scale both shapes, calculate the different pointwise descriptors in the different shapes, in the different scales, and then, through a learnable layer, downscale the descriptors by interpolating the best combinations of scaled descriptors. Then, the descriptors go through a deep ResNet-like structure where we refine the pointwise descriptors to learn the best C and C tilde. We then go through the original functional maps pipeline where we project the descriptors onto the spectral space, compute C and C tilde, reproject it back to the spatial space having P and P tilde, and propagate to our cyclic loss. The first experiment we have done, and this was as a sanity check to see that we can learn the right entities, was to optimize our network on an isometric dataset that we will present later on, and calculate the unsupervised loss that assume isometry while only optimizing our network. As you see in the table on the right, while not enforcing isometry, we were able to get lower loss values on the loss that assume isometry than the published results themselves, meaning that our network, without assuming isometry, was able to learn isometric structures inherently. The first dataset we evaluated on was the FAUST dataset, which is considered one of the most popular datasets for dense shape correspondence. The numbers in the table represent the average geodesic error compared to the ground truth correspondences. We compared ourselves to the top 5 unsupervised methods presented in the benchmark, as well as the deep functional maps pipeline presented earlier. As you can see, having best results among all testees. In all the visualizations that follow, similar colors represent correspondence by our mapper. Next, we also evaluated ourselves on the Tosca dataset. The Tosca dataset has completely different statistical attributes than the FAUST dataset. In terms of topology, the objects are completely different, number of vertices, density of points, and much more. Still, we only trained for a single epoch on Tosca using pre-trained weights from FAUST, having state-of-the-art results. The table on the right is similar to an ROC curve, meaning that the step function is the best result you can hope for, and we measure the number of ground truth correspondences while thresholding different distances from the ground truth. I must emphasize that we do not use any post-processing filters. Those filters are extremely time-consuming and usually improve results among all algorithms. Next, and this is the experiment before the last, we also evaluated ourselves against the partial correspondence dataset, a dataset that is considered extremely hard, as the target shapes has up to 75% less vertices than the source, with both partial and topological changes. Still, we were able to have state-of-the-art results among all unsupervised methods, as well as comparable results to algorithms that were tailor-made for the partial correspondence problem. Lastly, and to most emphasize the strongest point of our algorithm, we created a toy dataset. This toy dataset had multiple local, global, non-uniform scaling procedures and stretches. We did not present any of the samples of this dataset to our learner during training. We used the weights that were learned by the FAUST pipeline. Still, as you can see, in the examples in the middle, our learner was able to be completely a scale and stretch invariant, while we also evaluated on previous unsupervised results that do assume isometry between the graph. Those algorithms simply fail to calculate, to adhere such non-isometric constraints. To conclude, we presented the first unsupervised dense correspondence learner that is scale and stretch invariant. We do it using a cycle consistent loss that on the one hand does not punish on the difference in isometry between the graphs, but on the other hand incorporates the geometry of both shapes using the spectral decompositions. This understanding is what lets our learner a good initialization point and a regularization through the learning procedure. Thank you very much.
Okay, we have time for a couple of questions, and if the next speaker can come and set up his laptop. Okay, let's thank the speaker again.